All right, greetings everyone. Hope you are all doing well. Today we are moving on, getting even further into this limit stuff, and now start to look at a concept or a property of functions that limits will help us to define. Okay, so the first thing I want us to think about before I give you this definition is, what does it mean for a function to be continuous at a point? And I want us to just stop and think about this, because maybe some of us have heard this term continuous before. And even if you don't know what it means in the mathematical sense, maybe think about what it would mean just in the outside world, in the real world. What would it mean for something to be continuous? Maybe like never stopping, continually going, something along those lines, right? So that's what it means kind of in terms of English. So what does it mean for math? Well, we have this kind of strict definition if we're talking about something being continuous in terms of a function. So we said that a function f of x is continuous at a point A if and only if, remember that, we've seen that before, the following three conditions are satisfied. So there are three that have to be true. So number one, f of a, so the function defined at that point, or excuse me, the function with a input at that point has to be defined, so we have to get some sort of an output. The limit as x approaches a of f of x exists, and then the last piece is that limit has to be equal to what we get when we do the input of the function, or when we input the value a into the function. Okay, so down below I have two different types of functions, or examples of two different. I have a continuous one and a discontinuous one. And just to kind of show how this continuous function relates to the definition of continuity, let's say that my point A is right here. And let me try to draw that A better. Still not any better. One more time. Okay. So that's our point A. And let's look at where f of a is. So f of a, if we go up to the graph, be somewhere over here. So something like that, right? So first of all, it looks like f of a is defined, right? We can input the value a and we get something inside of that circle there that I just circled. So we have that first point we check off, right? Second one, the limit as x approaches a of f of x exists. So let's see, if we come from the right-hand side and from the left-hand side, does it look like the graph is approaching the same point from both sides? And hopefully you would agree with me that it does. So we get a check there. And the last one, does that limit equal the output value of the function, the value a? And it appears that it does. From each side, they seem to be converging towards this point where f of a is. So that's how we know that this is in fact continuous at this. So it's converging somewhere in here. Okay. So it also meets that last one. All right. What is it? So what happens if that doesn't happen, right? If we don't have all of these criteria met. So that's where we get something that is called discontinuous. So here we say that a function is discontinuous at a point A if it fails to be continuous, which means it's going to fail one of those three criteria. So let's look at this function on the right and see if we can figure that out. So first of all, is f of a, actually I'm going to choose my value a to be right here. So is the value a defined, or f of a defined? The answer to that question would be yes, right? See, there's this filled in dot here. So we definitely have that one. Does the limit exist? Well, as we come from the left, looks like we get closer and closer to this open dot value here. So we come from the right, then we're getting closer and closer to that closed dot value, but notice they seem to be separate, right? So that means that our limit from each side is different, which in that case, does the limit exist? No, it does not. So fails this condition here. So therefore, because it fails one of the three, if it fails any of the three, it is not continuous. So this is why this function is not continuous at this point A here. And then you'll notice here in both of these cases, we're talking about these functions being continuous or discontinuous as functions, not just at a single point. And so often when you hear something referred to as a continuous function, it means it's a function that is continuous at every point in its domain. So that's just a term you may see. The other thing I want to say about continuous functions, another way we sometimes define them, is as functions that can be drawn without kind of lifting our pens or pencils off the paper. Now, it's a very informal definition, but it seems to work. So if I look at this left-hand function, if I start here and draw along the graph here, notice that I never need to pick up my pen or my pencil to continue drawing it. Whereas with the one on the right, I can start tracing along, do my open dot, but then do the next part of the function. I actually have to pick up my pen and restart. Okay, so that's one way visually we can recognize that a function is continuous or discontinuous. All right. So let's apply that definition now to determine whether or not some things are continuous on a specific function. So over here on the right, we have piecewise function. We know it's piecewise because we see several different pieces in it. We're going to check whether or not it is continuous at the value x equals 2. So first thing they want us to do is find f of 2. So f of 2, here's the 2 here. If I go up to the graph, it looks like the output value there is 4. Okay, they want me to now find the limit as x approaches 2. So if I look at coming from the left and also coming from the right, it looks like the output values are approaching the same value, and it looks like they're getting closer and closer to 4 up there. And the last thing, check that the limit as x approaches 2 equals f of 2. Do we have that? Well, we have that the limit is equal to 4, and the output value of the function when we input 2 also looks to be 4. So we have that the limit is equal to that, so that would tell us that the function is continuous at that value 2. Okay. Another way to check that is to notice if I start, say, on the left of 2, and I start drawing along my graph there, and I get to where x equals 2, and then keep going, notice that I don't have to pick up my pen or pencil in order to draw that portion of the graph. So it's another way I know that the graph or the function is continuous at that point. Cool? All right, let's look at some other examples. So here, we're asked to check whether or not the function is continuous at x equals -1, x equals 1, and x equals -2. So let's do these one by one. So we'll start with, not that. We'll start with A here. So x equals -1. So we have to check those 3 criteria, right? The first one, does f of -1 exist? We're looking at the graph, it looks that it does, right? If we input -1, looks like we get an output of 1, so that's good. What about the limit as x approaches -1 of f of x? Does that exist? Well, coming from the left-hand side here, looks like we see that the output values are getting closer and closer to 3. And coming from the right-hand side, getting closer and closer to 1. So from the left-hand side, the limit is 3. The right-hand side, the limit is 1. So it actually, we end up with the limit there is d and e, so that limit does not exist. So therefore, because the limit doesn't exist, it fails that criteria. The function is going to be not continuous at x equals -1. Okay? So it fails that one there. All right, so let's look at the next one then. X equals 1 now. So looking here. So we have to again check those 3 criteria. So first of all, does f of 1 exist? It looks like it does, right? We can go up, input 1, we get an output of 1. does the limit as x approaches 1 of f of x exist? Well, coming from the left-hand side, looks like we're getting closer and closer to an output of 1. Coming from the right-hand side, looks like we're also getting closer and closer to an output of 1. So it does look like the limit exists there and is equal to 1. And the third criteria we have to check is, does that limit as x approaches 1 of f of x, does it equal f of 1? Well, the limit is equal to 1. The f of 1 is equal to 1, so it looks like it does match that criteria. So we see that here, because it matched all three of those criteria, the function is in fact continuous at x equals 1. And again, drawing along the graph there, we see that we can draw through the value x equals 1 without lifting our pens. So another visual way to check. All right, and the last one, x equals -2. So here, again, check our criteria. So f of -2, does that exist? Well, it looks like it does, right? Right here, we have that if we input -2, we get an output of -2. So that's good. What about the limit as x approaches -2 of f of x? Does that work? Well, let's see. From the left-hand side, if we follow along the graph here, it looks like the outputs as we get closer and closer to -2 are getting closer and closer to 2. If we come to the right-hand side, looks like they're also getting closer and closer to 2, so the limit there equals 2. So far, so good. We've met the first two criteria. What about the last one? So if we could limit as x approaches -2 of f of x, does that equal f of -2? Well, the limit we just found is equal to 2. When we input the -2 into the function, we got an output of -2. Are those two the same? No, they're not, right? So those are not equal, so therefore it fails that condition. So we know that at x equals -2, that the function is not continuous. Okay, so for x equals -1, we saw not continuous, x equals 1 continuous, and x equals -2 not continuous. All right, let's look at this function now. So we're looking at the function h of x equals x squared minus x minus 2 all over x minus 2. And we have to check whether the function is continuous at the value x equals 2. Well, notice if we start to go through our criteria, so we start with that, finding h of 2. If I plug 2 into this function, I'll have 2 squared minus 2 minus 2 all over 2 minus 2. Hopefully almost immediately you see a problem down here in the denominator, right? If we do 2 minus 2, we'll be dividing by 0, which is not allowed. So that means we would get h of 2 does not exist, right? So therefore, that would fail the first criteria for something to be continuous. So we know then that the function will not be continuous at the value 2. However, watch what happens if I do this. So I'm going to take that x squared minus x minus 2 over x minus 2. And looking at the top there, I think that this part factors. What do you guys think? Well, let's take a look at it. If I do rewrite this as x minus 2 times x plus 1 for the top over x minus 2, is that top part the same? X minus 2 times x plus 1, is that the same as x squared minus x minus 2? I think that it is. And notice then I can cancel out the x minus 2, so then I get that this function comes out to be x plus 1. And that function, x plus 1, that function is continuous at x equals 2, right? I can go ahead and just plug 2 in there and also check that the limit exists and that the limit equals what I get if I input 2 into the function, right? So what is going on here? Well, you'll notice looking at the graph over here on the right-hand side, right, that this is an example of a function where the limit looks like it exists from both the left and the right, right? See, as we come from the left, looks like that output value is getting closer and closer to 3. Same thing as we come from the right. And really all that's missing is that hole there. So when we have an example like this, we call that a removable discontinuity. And let me say a little bit more about that on the next slide. So here's like the official definition of a removable discontinuity. So the first things first, notice that it says that if f of a is undefined. That's a really important piece, because if f of a is defined, like on the last one, we actually couldn't put 2 into the function, right? Because it caused there to be a division by 0. So it was, f of 2 was undefined, but if we can plug in 2, or plug in whatever the value of a is and get something, then this definition doesn't apply. But here it says if f of a is undefined, but the limit exists as we approach a, then we say that f has a removable discontinuity at x equals a. So that's the official definition. And really important here, when we say that the limit as x approaches a of f of x exists, we mean that that limit is equal to some number L, okay, where L is a real number. I should also say L is not some sort of infinity there. It's just a number like 3 or 4 or -1 billion or something like that. And then the other thing I want to say about this is this term removable discontinuity. Why is it called that? Well, the reason is because often when we look at the graphs of these types of discontinuities, and for example, if I go back to this one, what we really see is that there's just a little hole in the graph there. Okay, and it's not like there's some hole or some dot up here or dot down here that's taking its place. There's just a hole in the graph. So theoretically, if we wanted to, we could fill in that hole and then our function would be good to go. So that's why we call it removable, because we could just kind of like take a marking pen, fill it in, and be good to go. Now we can't do that, obviously. We have to mind the fact that it's missing. But if that's all it takes, we call it a removable discontinuity. All right, let's look at another type called a jump discontinuity. Does anyone have any ideas why these are called jump discontinuities? Yeah, you guys are right, because it looks like the graph is jumping from one point to another, right? So you can imagine looking at this left-hand one. If I'm going along the graph here, but not like that. If I'm going along the graph here, just tooling along, okay, and I get up to this point here, well, to get to the next part of the graph, I'm going to have to jump. So imagine this is me jumping to get to the next part of the graph, and then continue on my merry way. Similarly, that happens with the one here in the middle, right? So we're going along here, we get to here, then we jump up to the next part. And this one here we actually see has lots of jump discontinuities, this third one, because we go along, jump, go along, jump, go along, jump, so on and so forth, right? And notice in all cases for these jump discontinuities, the function is defined at the number where the jump discontinuity is happening, right? So here we see a closed dot, here we see a closed dot, at all of these we see closed dots. So the function is defined. The limits doesn't exist, right? Because in each case we're getting a different limit from each side. But it does exist from each side, right? So we have one limit coming from this way, one limit coming from this way, one limit coming from this way, one limit coming from this way. But those two limits are different, right? So that's what makes this not continuous. But again, that's what makes it a jump discontinuity. Okay, so here's kind of an official definition. A discontinuity or jump discontinuity is a discontinuity where the value of the function jumps from one piece of the graph to the other. It can also be said as discontinuity where both the right and left limit exist, but they are not equal to one another. And looking at this graph, I may have misspoke. Here it looks like this is an example where the value of the function at a particular point does not actually exist, as we have two open dots. So maybe what's more important is the limit is different from each side. It exists from each side, but it's different. All right, and then one more type of discontinuity is what we call an infinite discontinuity. So we say that a function has an infinite discontinuity at a point if the limit as we approach from the left to right equals plus or minus infinity, or if the limit coming from the right-hand side of the function is equal to plus or minus infinity. We've looked at a couple of these already, but just notice over here in the graph, we see that as we come from the left-hand side, the graph shoots up and is going towards positive infinity. So that would be an example of this one here, where from the left-hand side, we're going to positive or negative infinity. And then we can also have what we have here on the left-hand, or the right-hand side, where it's shooting down towards negative infinity. And so that's the second part there. Now I will say to have an infinite discontinuity, notice that it has that word or in there, so it doesn't have to be going towards infinity from both sides. So as an example of that, you might have a function that could look something like this. So let's say it is some sort of a square root function that maybe starts here with an open dot, and then we see some sort of an asymptote here, and then on the other side we see that the graph is doing something like this. Okay, well, notice on the left hand side of the graph there, right here is where the function is diving down towards negative infinity. But on the right hand side right here, it shows the function is not defined. It kind of stops there, right? So that would be an example of where we have an infinite discontinuity, but it's only on one side of the value we're approaching. Cool. All right, one last example for this video. Let's say our function is f of x equals 5x plus 30 if x is less than negative 5, square root of x plus 30 if x is greater than negative 5, and 2 if x is greater or equal negative 5. So notice here we have a piecewise function. Again, we know that because it has different pieces. And so we need to determine whether each of the following statements is true or false based on what we see. And we'll justify our answers, which means we'll explain. So first one, f of negative 5 is defined. Is that true or false? Well, if we plug in negative 5 here, so if we do f of negative 5, are we able to get an answer? It looks like we do, because they tell us right here that the output is 2 if x equals negative 5, right? So f of negative 5 should be equal to 2 based on what we see there. So it looks like, is f of negative 5 defined? The answer there would be true, right? Okay, now let's look at the limit as x approaches negative 5. Does that exist or not? And remember, if we're thinking about that, we're thinking about on a graph, if we have negative 5 here, you want to know from the left and from the right, are we approaching the same values, right? So we want to know as we come from towards negative 5 from the left-hand side and from the right-hand side, or from below and from above, do we get the same thing? Well, let's take a look at what the function tells us. So notice here, we are told that for values of x less than negative 5, we use the function 5x plus 30. And so something we can do, I'm sorry, I'm going to clear some stuff out here. Just don't know this is true. Is let's look at the limit as x approaches negative 5 from the left-hand side of f of x. Well, coming from the left-hand side, the function we use is 5x plus 30. And notice -5 is in the domain of that function. So we can just plug it in to find the limit. So we do 5 times -5 plus 30. 5 times -5 is -25 plus 30 gives us 5. So it looks like the limit exists from that side. If we look from the other side, so the limit as x approaches -5 from the right-hand side now, well, that tells us to use the other function. I'm sorry, I'm kind of bouncing around here. So this is going to be the limit using the square root of x plus 30 now. And we're still looking at this x approaches -5. Notice that -5 is in the domain of that function, so we can just plug it in. So we would have the square root of -5 plus 30. Skip a couple steps there. We'll see that'd be the square root of 25, which again gives us 5. Oh boy. Okay. So notice for both limits, we got the same thing, right? From both the left-hand side and the right-hand side, we got that the limit was equal to 5. So because they're the same from each side, then we know that the limit exists there, right? So I'm going to say, again, this one was true. This one's also true. All right, now, third piece. Does the limit as x approaches -5 of f of x equal f of -5? Well, we just saw that the limit was equal to 5. However, in the first one, we saw that if we evaluate the function at -5, that is equal to 2. And notice those are not the same thing, right? 5 does not equal 2. So therefore, this one is actually false. And now that we have those first 3 answers, that can help us tell us what we need to say for the final 2. So is the function continuous at x equals -5? That would be false, right? Because it fails that third criteria. The limit from each side does not equal what the function value is. And then the function is not continuous at x equals -5. That would be true, right? Because it fails that last criteria. Now, a question to keep in mind. Is this a removable discontinuity? We saw that the function, or the limit, was the same from each side, so the limit exists. Would it be removable? No, you guys are right. It would not, because the f of -5 existed, right? This was not undefined. So, not a removable discontinuity by our definition. Okay, that's it for now. Thank you guys for your attention.